Okay, so capacitors. We're going to see capacitance because, again, all this stuff is going to build up to the nervous system. So let's just define capacitors. I think you had a quiz question about capacitors, is that right? Yeah. Capacitor is a device that separates positive and negative charges. Gosh, that took 40 minutes? Sorry. All right, it typically consists of two parallel plates that are separated by an insulator. So this is a figure of a capacitor. Two parallel plates, that means they don't touch. And in order to keep them to not touch, usually we put something in between them, some sort of insulator. Usually, actually, with a capacitor, is they'll take, I'll show you a video a little later, but they take two metal plates, and then they put a piece of wax paper in between them, and then they roll it up. So the metal plates don't touch. They're separated by an insulator. And then you have this nice little compact device that you can put into a circuit. Right? It's kind of like, y'all remember roly-poly when it was here? It was at, it's like a phone store now, and before it was like a Chubby's, and then before that was a roly-poly. At 7. You know what I'm talking about? Yeah, it's like a roly-poly. It's like a tortilla with meat in between, you roll it up. Yeah, roly-poly's food.
Yeah, it's a sandwich.
Yeah, where you been?
I lived here my whole life. I have no idea.
You remember the Chubbies? Yeah. It was at 7th and Canal.
Okay.
Where the Chubbies was, which is an unfortunate name for ice cream.
Oh, yeah, I know what you're talking about.
Okay, so when it's connected to a source of potential, electrons will travel from one of the plates to the positive terminal. So what I'm going to have here is I'll have electrons that were on this side, and they'll move over to the positive terminal. Because if you remember electrons, when we're thinking about our mountain, remember electrons move from low to high potential, right? These are electrons, and the positive side of the battery is the high potential side. And so my electrons are going to move from where they have not very much energy to where they're going to have more energy. Okay, they're going to move from low to high potential. So those electrons, remember that negative charges move from low to high potential. And when those electrons move away, we're going to leave this side over here with what kind of charge? A positive charge. Right, that's how I make positively charged objects, not by putting protons onto them, but by taking away electrons. Because it turns out protons are pretty hard to move around, because they're tightly bound up in their nuclei. So, when I take away those electrons, this side is going to be really positively charged. So that plate is positively charged. And then because that plate is positive, electrons from the negative terminal will travel to the other plate. So then my electrons will come up here, and they'll travel to this plate, giving us a negative charge on that side. So then each plate has equal but opposite charges. I'll have one plate over here with, say, 5 positive charges, and one plate over here with, say, 5 negative charges. And then, you know, we saw this figure on our quiz. We can talk about how charges move back and forth between these two plates. This is a capacitor. I'm going to have positive charges that will move in that direction. Negative charges will move right to left. And then I can also talk about my electric fields. What is the direction of the electric field on this figure? It's to the right. Yeah. So my electric field is going to be in that direction. If I have a positive charge, it's going to move along the electric field lines. If I have a negative charge, it moves opposite the electric field lines. And you can see that either by thinking about the electric field lines, or you can think about, well, the positive is attracted to the negatives, the negative is attracted to the positive charges. So we can describe the capacitor. I like to think of the capacitor as like a big bowl. And that bowl can hold so much, I don't know, popcorn or whatever, or cookies, or whatever it is that you like to eat. Cookies. It has lots of cookies. And so I can only fit so many cookies into that bowl. And the capacitor is sort of a similar way, except instead of cookies, we have charges. And the capacitor can only hold so many charges. So the capacitance of the device describes its capacity to store charge. And we'll have two measurements of the capacitor. We have one is the area of the plate. And two, we have the distance between the plates. Now, let me ask you a question. If area goes up, what happens to the capacitance? Does the capacitance go up, down, or stay the same? A, B, or C? Just what do you think? If I increase the area of the plates, what's going to happen to their capacity to store charge? Will the capacity to store charge go up, go down, or will it stay the same? If I make those plates bigger, will they hold more, fewer, or the same amount of charge? We haven't said this, just what's your intuition on it? All right. Yeah, the area of the plates is A. I'm going to stop at 38. 38. 2 more seconds. Okay. So your intuition for most of you is right. That if I make the bowl bigger, it holds more cookies. And if I make the area of the plates bigger, they just have more space to store charges. So if the area goes up, then the capacitance goes up. Let me ask you another question. What if the distance between the plates goes up? What happens to the capacitance then? Will it go up, down, or stay the same? That is, if I pull those plates farther apart, they're hooked up to a battery, remember, and that battery is supplying those charges. But what if I pull them farther and farther apart? What happens to their capacity to store charge? Will it increase, decrease, or stay the same? It's a little less intuitive, so it might not be clear to you, but just, you know, yes. All right, let's stop at 32 or 33. No, we'll go to 40. Go to 40. Oh, good. Was this on the quiz? No? All right, good. B is right. That if I pull those things farther apart, it's like I'm spreading energy over a larger area. That is really what I'm doing. And when I spread that energy out, it gets thinner and thinner. I'm not able to store as much charge. There's just not as many charges go onto those plates. So if D goes up, then C will go down. It's an inverse relationship. And can I tell you a middle school joke? It's okay to tell middle school jokes in this class, right? Okay. Have you, sorry. Have you heard of this new movie called Constipated? No. It hasn't come out yet. I'm sorry, that's bad, right? Is that bad? Okay. Yeah, everybody's heard that one, Julian. So C is proportional to the area, and C is proportional to 1 over the distance. Okay? We, it's like a fish. Um, so C is equal to A over D. But we have, as usual, we have some coefficients. We have epsilon naught. That's called the permeability, or was it permeativity? Permeability of free space. It's just a constant. Don't worry about what it is. It has a very small number. It's like 8.85 times 10 to the minus 12. I'll give it to you. 8.85 times 10 to the minus 12. But you're never going to have to use it on a test or quiz or anything. And that has value of farad meters, I guess? Yeah, farad meters. FM. Also, we will have another constant. This looks like a K with like a curly K. It's the kappa, lowercase kappa. Whoa. So, epsilon, this is just a constant. Don't worry about it. Do worry about this, though. Kappa is the I did not erase anything.
No, I didn't leave an erase with the paper.
I left in a space. Kappa is the dielectric constant. It is determined experimentally, and it's always greater than 1. I'll tell you what it is. So, when I have this capacitor, remember, we put an insulator in between them. The insulator, it has a constant that's described by kappa. That dielectric constant describes how good of an insulator it is. And the better the insulator, the more charge I'm going to be able to store on that capacitor. So that little piece of wax paper that we put between those two pieces of metal, it not only keeps the plates from touching, because if the plates touch, you don't have a capacitor anymore. The capacitor, the plates have to stay separated. But it also increases the amount of charge that we can put on the capacitor. Okay? Eventually, if you have a capacitor that's like this and you put charge, the little charges are going to start jumping across that space, right? Just like with the Van de Graaff generator. I brought that in, right? Yeah, with the Van de Graaff generator, the charges will eventually jump across that space. And so the insulator prevents that from happening and allows you to put more and more charge on it.
That's just what it's for. Just put more charge.
Yeah, so the dielectric has two purposes, to keep them from touching and to store more charge. Let's write that down. It might come up later. No, I'm not even going to write it down. But the purpose of a capacitor is to store charge. And when you store charge on a capacitor, that allows you to have energy that can be used for later. Capacitors are quite useful in circuits. If you have like one of those cars with the boom, 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 you know what I'm talking about? Anybody have one of those? It's okay. Huh? Yeah, like with a really fancy stereo. When I was in high school, do you seriously?
Yeah.
Are you serious?
Yeah, look at it.
So with the really nice systems, they have capacitors in them. They store, you get these big old capacitors, like people that go to competitions, they'll get these big old capacitors, and what they do is they store up energy until they need energy for a big punch, like in their base, and then when they get that big punch, it'll release that energy into the system and allow them to have that big bass sound. you have big capacitors in your?
I don't know what that means.
Okay. You would know what they had.
A thing. I guess. I don't know.
A subwoofer? Yeah.
I don't really know what kind or what it is.
Okay.
I should know.
Anyway, capacitors are used to store energy. When you connect a capacitor to a battery, we can calculate a couple of things. The charge on that capacitor is equal to C times V, where remember, C is the capacitance, V is the voltage, or the potential difference. That's what you have off the battery. And then U, what is U? You'll recall? Is energy, potential energy. This is potential energy. And Q is charge. U is also proportional to C and V, but it's a little bit different. It's 1/2 CV squared. All right? So for example, if I have a capacitor, Q is equal to C times V. If I double my voltage, I'm going to double the amount of charge. Because when I double the voltage, I'm doubling the amount of energy that's being fed into this capacitor, and it's going to be able to dump more charges onto that capacitor. All right, let's give you a question. So let's say that I have a capacitor circuit that looks like this. By the way, this is the symbol for a capacitor, and this is the symbol for a battery. I don't know if we've seen those yet. I don't think that we have. Capacitor just looks like a capacitor, two parallel plates. The battery looks a little similar to the capacitor, but I want to show you that one side is longer than the other. Okay? And this corresponds to the positive terminal and the negative terminal, because one of them has more energy than the other. Sometimes on circuit diagrams, you'll see a positive here and a negative here. So on your 9-volt battery, for example, the big side is the big round thing. I think that's the positive terminal. And the small side is the smaller round thing. All right, one's high potential, one's low potential. And then our capacitor, like I said, just looks like a capacitor. Well, let's say that we have, I don't know, 24 volts on this capacitor, or 24 volts on the battery. And I increase, or I decrease V from 24 to 6 volts. The charge is initially 16 microcoulombs. What is the new charge? Gotcha. I decreased V, it was 24 volts, and I had 16 microcoulombs. Now I decrease it to 6 volts, and what is the new charge going to be? Huh? Look, you know that Q and V are related by this expression. And so whatever I do to V, I'm also going to do to Q. And so what have you done to V going from 24 to 6 volts? By how much have you decreased it or increased it? And then you do the same thing to the charge.
Is that micro?
Yeah, it's a micro. It looks like an M, but it's really a U, and it has an extra little curly thing to the left of it. Or micro means 10 to the minus 6. That was from chapter 0.
Yeah, I know what I thought it was an M.
It looks like an M, sort of.
I was just making sure that's
I told you I've been taking Hebrew, right? And in Hebrew, yeah, a lot of the letters look the same. And in fact, when they were copying old Hebrew scripts, they would often mess them up. Not often, but sometimes they would mess them up. And this went on for thousands of years, that the Jewish scribes would copy the Old Testament day after day. Thousands of years they did this. And it was hard because, it was all by hand, and the letters all look the same, and there's no punctuation. They don't have any spaces between the letters. Like the words just all run together because they didn't have much paper to write on. They just had there were no spaces between the words. And they had no vowels either. It wasn't until, like, I don't know, AD when they actually started adding in vowels to help people understand what the words were better. But in all those thousands of years, those scribes, they really only messed up like 3 or 4 words. Isn't that amazing? Like all that copy. And those words were kind of inconsequential anyway. Isn't that amazing? And we can't even tell, is that a mu or an M? And they had very similar things. All right, we ready? Wanna... Oh, it's not an attack on you. It's remarkable, I think. 250 will stop? 250? What? Okay, D is right. So if I'm changing my voltage from 24 to 6, that means I'm dividing it by a factor of 4, right? Because 24 times 1/4, that's equal to 6. And then whatever I do to that, I also have to do to the charge. So my charge was initially 16, and I multiply it times 1/4, so it's equal to 4. So 4 is the right answer. Okay, so the sodium-potassium pump does not use a capacitor. Like, it's not a capacitor that we would use in a circuit, but there is a potential difference between the two sides of the cell membrane. All right, voltage. Those are mostly the same. And we sometimes talk about that potential difference because, in the cell membrane, you have the cell membrane right here, and then you have positive charges on one side and negative charges on one side. What is this but a capacitor? The separation of charges. And so sometimes we talk about our cell membrane as if it's a capacitor. And sometimes we'll even calculate what is the capacitance of the cell membrane between those charges. So there is also a capacitor of sorts set up between the two sides. It's a lot like a capacitor because it's separating the charges. And so if you know the capacitance of the cell, that is, if you know the area, if you know the distance between the two plates, or the distance between the two sides of the cell membrane, which is basically the width of the cell membrane, and you know the kappa, which is how good is the cell membrane at insulating between those two sides, then you can calculate the charge involved. You guys probably won't ever see that. Y'all don't talk about that in AMP, do you? Like capacitance of the cell membrane? If you go to graduate school, maybe some of you will see that, but probably not. But it's still kind of interesting that we can talk about the cell membrane like it's a capacitor, as we have these charges moving back and forth. And your book talks about that too. We have some examples of capacitor use. Flash on a camera. Actually, I don't know if camera flashes use these anymore. Like the really nice cameras do. And if you probably never used like the old film cameras that made the sound. whenever the flash would go off, you know what I'm talking about? That has a capacitor in it. It stores up that charge until you're ready to take the picture. Click, ding, and then the capacitor discharges through the filament of the light bulb. But I think today with LEDs and other lights that we use, you don't need as much energy to produce the same amount of light. And so they probably don't use capacitors. A flashing light, those can use capacitors. Capacitors store up energy, and then they expend the energy. They store it up, they expend it. We didn't talk about this, but another great use and common use of capacitors is for things that are repetitive, that repeat over and over. Because capacitors repeat, they have a very set time that they charge and discharge, and we're not going to get into that. But it allows you to have things that are flashing. Like on your car, when you turn on your flashers, those use capacitors in the circuit. It goes click, 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 click. So next time you're with your friends driving around and you use your flasher, you say, hey, I have capacitors working in my car. You hear them? Click, click. Okay? Those are capacitors at work. And then also keys on a keyboard. This is kind of interesting. So a key on a keyboard, there's my key. It is actually hooked up to a metal plate. I have a metal plate right there. And then below it, there is another metal plate. And when I come in and push this key, then it changes the distance between the plates. D, when I push on the key, it decreases D, and it changes the capacitance of those two metal plates, and that's worked into a circuit that tells your computer that, oh, they're pressing the R key, or they're pressing the enter key. It's a capacitor. Didn't know that, did you? I have a video I want to show you. It's from MakeZine, which is kind of like a DIY, I like to build stuff kind of magazine. And he talks about capacitors. He builds one. That's a good, if you have a middle schooler or maybe even elementary schooler, it's a good project for them to do as a science fair project. There are some things that you can change about it to change the amount of charge that it can hold. By the way, the very first experiments that were done on electricity in mammals, or I guess amphibians, I think it was frogs they used, right? They put electricity through their dead limbs and make them move. You know what I'm talking about? How they make the frog legs move on dead frogs. Study that in biology? No, they don't do that here. But anyway, they use capacitors as a source of the electricity because at that time we just didn't have batteries like we have now. So let's look at current and resistance in about 7 minutes. So current is the flow of charge. It's sort of one of our big basic ideas that falls along there with voltage. So it's Q divided by T, or charge over time. So if I'm thinking of a wire, here's my wire. I can think about I have all these electrons that are in the wire, and they will move through the wire. It's sort of right to say that they move through the wire. Really, it's the energy moves through the wire, and it's passed along by the electrons. But we'll just think of the electrons actually moving through the wire, and they're moving through with a certain charge per unit time. That is coulombs per second. Remember, C is coulombs per second. Usually, this refers to electrons moving through a wire. Though it can refer to any flow of charge. So when they're doing various experiments, like at these big particle colliders, when they have charges that are moving in these big circles, they'll talk about the current. Even though it's not in a wire, that you just have charges moving in space, that anytime you have the flow of charge, we call that current. The unit is a unit you've seen before. It's an amp or an ampere. Amp. It's abbreviated with a capital A. It's a person's name. And then that's current. And then a resistor is a device I think this was on your quiz, if I'm not mistaken, right? Resistor. A resistor resists the flow of electricity or limits the flow of electricity. Or you can think resist. And you can think about a resistor like as a pipe with water flowing through it. In fact, it's a pretty good analogy when we're talking about circuits to think of circuits as a system of pipes and pumps that pump water through those pipes. And when you have constrictions in the pipe, smaller areas, that's like a resistor. It causes tension and resists the flow of the fluid through that system. Your pipe is defined by two qualities. Just like with the capacitor, which was defined by the area and the separation, if I have a pipe or a resistor, it's defined by two quantities: the length of the pipe and the cross-sectional area. So, is it more difficult to push water through a long pipe or a short pipe? Through a long pipe, right. So if you're trying to push water through a big old long hose, that's harder to do than with a short hose. That's why if you're trying to siphon gas out of a vehicle, I've done that before? No? You have a little section of hose. When I was a kid, we would run out of gas a lot because we were kind of poor. So we always kept like a little section of hose behind our seat. That way if we needed to siphon gas off of some other vehicle, not steal it, mind you, but if we needed to take gas from my uncle's truck, then we could just grab the hose and say, "Hey, Uncle MacD, we're going to get some gas out of your truck." He's like, "All right." And then you stick the hose down into the gas tank. Y'all done this before? And then you have to sort of stand down like this. You done this, Katie? And you put your mouth on the hose and you sort of suck up a little bit, and it's practice because you don't want to get gas in your mouth, right? And then you get it started, and then you put it in the gas can. You've done that? Yeah. Yeah, I'm from Mississippi. It's about the same. So, all right. So anyway, you want to have a short pipe. You don't need like an 8-foot hose in the back seat of your truck to siphon gas. You just need a little short section because it's easier to draw that gas up into a shorter pipe. Do y'all not do that in Texas? Not. Oh, okay. And then what if my area gets bigger? So if the area gets bigger, what happens to the resistance? Is it easier or harder to push water through a bigger pipe? All right, let's think about it. What if I make the pipe really small? Is that easier or harder to push water through a smaller pipe? It's harder. So if our area goes up, that means that our resistance goes down. So if our length goes up, that means our resistance goes up. And notice I have two relationships, one direct, one inverse, just like we had with our capacitor. And so I'm going to leave some space here. Megan. R is equal to L over A. And then, as usual, we'll have a constant, and here, rho, R-H-O, it's a Greek letter, is the resistivity. It is different for different materials. Wood, for example, resists the flow of electricity a lot, so it has a high resistivity. What's some things that have low resistivity? Things that don't resist the flow of electricity, for example. Metal, like copper. That's what you use in your house. Has a very low resistivity. Oh, let's get these last two little things in, okay? The current is dependent on both the resistance and the voltage. And the relationship between those is going to be I is equal to V over R. And this is what we call Ohm's law. And this is the last thing, V is equal to IR. We'll touch base with that on Tuesday. Oh, actually, check your emails in the next day or so. We might not have class on Tuesday. I'm sorry, I have a meeting at Institute. So, I'll let you know. I'm really sorry, but I will let you know over email. Don't assume that we're not having class unless I email you. But I'll email you regardless. Have a great day.